Very good evening, children. Today I would like to say about algebraic structures and morphisms. In these algebraic structures and morphisms, we have the topics algebraic structures with one binary operation, semigroups, monoids, groups. Already I told about all these, isn't it? Already I said algebraic structures with one binary operation, group, semigroup, monoid. These all are comes under this. And finally, we got information about abelian group also. Then while coming to the two operations on one set, we have rings and fields. Those also we have discussed. And about properties of group we discussed and theorems on that. And substructures means subgroups and normal subgroups. These also I covered. And next, algebraic structures with two binary operations under that rings and integral domain and fields. These are one category. Boolean algebra and Boolean ring. These all are about the Boolean algebra. Already we studied in the third unit. And again I will give the information for this. And identities, which are the identities? Same like commutative, associative, De Morgan's. Those all here also we have. Duality concept we covered in the third unit. Representation of Boolean function I would like to say then disjunctive and conjunctive normal forms I said in third unit. Now I would like to start about fourth unit. So in this algebraic structures and morphisms unit name, we have first thing, what the name itself is algebraic structures and morphisms. What is an algebraic structure? How can we define? So here for defining algebraic structures, we need to take a non-empty set and some operations that must be most probably binary operation we can take. So one non-empty set and one binary operation is called combinedly, and operations and some identities. Operations means by using operations, binary operation one only we are selecting. By using that particular operation on that particular set, using some laws, identities, we can define a algebraic structure. That means an algebraic structure consists of non-empty set, a collection of operations on a finite arity means binary. Particularly binary typically we can use always, most probably binary operation only we can use, and a finite set of identities. Finite set of identities are axioms. These are the rules we have to take on that particular thing. So this is the definition of algebraic structure. And what are the types of algebraic structures? I said that one operation on one set. So for that we have examples, groups, semigroups and monoids. Most probably we have these only in our syllabus. Next, quasi-groups and loops also comes under these, and I given definition for those. These are like groups only, except some operations need not be associative. Some operations need not be associative. Sometimes associative operation is not there, but it is a group. So at that time that is called as quasi-groups and loops. And while coming to the magmas, these are the like groups only. These are like groups only, except the operation need not be associative or have inverse element. Need not be associative or have inverse element. Need not be associative or not have inverse element. Associative not satisfied, or maybe inverse element not be there. That is comes under magmas. So these are the special kinds of groups. And while coming to the two operations on one set, the best example is ring. Non-associative ring means that not satisfies associative operation. Semi-ring means only closure and associative properties by product operation. And nearings also. Non-associative rings. Multiplication operation need not be associative. That is non-associative ring. Already I said semi-ring means these are like rings, but addition operation need not have inverses. In addition operation, there is no inverse for all elements. That is called as semi-ring. Next one is near ring. Addition operation need not be commutative. Tell that That means near ring means addition operation, not commutative, not abelian group. Addition operation. And while coming to the lattices, two operations are usually called meet and join. Latticate means meet and join commute but need not be associative. What about meet and join? That you have to know. You must have an idea what is meet and what is join. Join and meet means, here I wrote a lattice can be described using two binary operation. Join and meet of two elements. The join is the sum and join or sum, or else we can denote this by SUP and we can read it as supremum. And the meet means product of two elements is greatest lower bound, GLB. This is like LCM, join is like LCM, and meet is like GCD. See, in this table here we are taking XOR operation plus union, not OR. We are putting a circle means that is not OR operation, NOR. We can call that as NOR operation. And here plus union. A join B means LCM of A comma B. Okay, A meet B means GCD of A comma B. Here we can take any operation as star and multiplication operation, then intersection. That means meet is comes under product. Join is comes under addition. Likewise, not only addition, union and addition. And here intersection and product. Star may be any operation. While coming to the join, only XOR we have to take as first operation, then plus, then union. Likewise, we can understand. Next, we are going to read about algebraic system. What is the definition of algebraic system? A set A with one or more binary operations defined on it is called an algebraic system. We can denote like this. A set A with one or more binary operations is defined on it is called an algebraic system. While coming to the general properties of algebraic system, first property is closure property. Here we can take star B any binary operation on a set A. The operation star is said to be a closed operation A if A star B is equals to belongs to A for all A comma B belongs to A. The meaning of this is whenever A comma B is there in that particular group, okay, and the operation on those if we do, the result will also be in that particular group. If A comma B in that group, A star B is also must be there in that group. For all A comma B, there must be A star B. The result value must be comes under that particular group only. That is called as closure property. And next one is associative property. Let star be a binary operation on a set A, then the operation star is said to be associative if A star B of star C is equals to A star of B star C for all A comma B comma C belongs to A. These all we know. Very familiar thing is associative property. Next one is identity property. There exists an element E such that A star E is equals to E star A is equals to A only. That means if we add 0 to any number, we will get the same answer. Likewise, 0 is the additive identity. If we multiply 1 with any number, we will get same number. A star 1 is equals to 1 star A is equals to A. 3 into 1 is equals to 1 into 3 is equals to 3. So, 1 is the multiplicative identity. Likewise, next one is inverse property. Here, we must have an identity. Then, we can say that any two elements by operation, we will get identity as result. That means A star E is equals to E star A is equals to A. Likewise, any element B such that A star B is equals to B star A is equals to E we have to get. E as the result we have to get, then we can call B is the inverse of A. A inverse is equals to B, we can say that. These four properties needed for group. If we call any algebraic system as group, these four conditions must be true, must be satisfied, must be held by that particular set. Next one is commutative property. If A star B is equals to B star A for all A comma B belongs to A, that means A star B is equals to B star A for all A comma B belongs to A. Whenever 2 into 3 is equals to 3 into 2 is equals to 6. Likewise, 2 plus 3 is equals to 3 plus 2 is equals to 5. Like that. So, there must be commutative property. Then that particular group is called as abelian group. Semi-group means till associative. Closure and associative properties are held by that particular algebraic system. Then that particular algebraic system is called as semi-group. And while coming to the monoid, algebraic system which holds properties like closure, associative and identity. Properties like closure, associative and identity, that is called as monoid till third property. The extra property here is identity property. And next one is group. An algebraic system G comma star is said to be a group wherever these four properties are satisfied. Then that particular group is called as, that particular algebraic system is called as group. And while coming to the abelian, including those four properties, another property is commutative if holds. If it holds, then that particular algebraic system is called as group and abelian group also. So this is the information about group definition. Till group definition we finished. And next one is properties of group. What are the properties of group? Identity element is always unique in that particular set. Only one identity exists in a set. And next one is inverse of an element is unique. Every element have different inverses and only one inverse for one element. That is the second property. And cancellation laws, you already studied about cancellation laws in degree level only. Left cancellation law, right cancellation law. These are the left and right cancellation laws. Next one is order of a group. The number of elements in a group is called as order of a group. Finite group means if the order of a group G is finite, then G is called a finite group. Number of elements are countable. Knowingly we can say that how many are there. That is finite. If we cannot say how many are there, that is infinite. Okay. Now I am going to continue with a problem I am taking differently, which I didn't said in the classroom. I am selecting if M is a set of all non-singular matrices of order n by n, then show that M is a group with respect to matrix multiplication given that. And is M comma star an abelian group or not, we have to justify. Now I am taking non-singular matrix means here mod A not equals to 0. That means in case 2 by 2 matrix, if we take AD, if 2 by 2 matrix we take AD minus BC is not equals to 0, then that is called, that particular matrix is called as non-singular matrix. Now here I am taking A, B, C belongs to M. 3 matrices I am taking A, B, C. And we are going to check with closure property. Product of two non-singular matrices, again a non-singular matrix we have to get. Non-singular means which mod A or mod B or mod C is not equals to 0, then those three matrices are non-singular. Here we are taking. In case if we take product of A and B, AB also must be non-singular matrix. That is the thing we are going to do now. Next here, if we select two matrices, the product also not singular. So we can say that AB belongs to M for all A comma B belongs to M. So that's why here, that is why closure property holds by that particular matrix set. And next one is associative property. Product of any three matrices is holding the property of associativity. Next one is identity. We know that I belongs to M. I means identity matrix. 1001 is the identity matrix. I think you already familiar with all these things. Now here if we take that identity matrix is as identity element in that particular matrix set. Identity element is 1001 matrix. And next one is inverse property. If we take A into A inverse is equals to I, we already know about these things. So we can write like this. Then we can say that matrix multiplication is a group. But multiplication is not commutative. Matrix multiplication is not commutative. AB is not equal to BA. That is why matrix multiplication is not an abelian group. So for proving matrix multiplication is not commutative, for that purpose I am taking two matrices here. A is equals to 1, 2, 3, 4 I am taking, and then B is equals to 4, 5, 6, 7 I am taking. Then A into B is equals to first row, first column 1 into 4 plus 2 into 6, 1 into 5 plus 2 into 7, then 3 into 4 plus 4 into 6, and 3 into 5 plus 4 into 7. Then 1 4s are 4 plus 12, 5 plus 14, 12 plus 24, 15 plus 28, which is equals to 16, 19, 36, 43. Here we got like this. Okay. Now we are doing B into A, which is equals to 4, 5, 6, 7 into 1, 2, 3, 4, which is equals to 4 1s are 4 plus 5 3s are 15, 19, 4 2s are 8 plus 5 4s are 20, 8 plus 20, 28, 6 1s are 6 plus 7 3s are 21, 6 plus 21 is 28, 27, and 12 plus 28, 12 plus 28 is 40. So these two are different answers. That is why matrix multiplication not hold the property of commutativity. We can write like this.